Ωραία, ωραία. Λοιπόν, οκ, ξεκινήσαμε. Οπότε μπορείς να ξεκινήσεις, Πιέρο, όποτε θέλεις.
Για να δω. Βλέπετε όλα έτσι. Φαίνεται όλη η οθόνη, να φανταστώ.
Ναι, μια χαρά, μια χαρά.
So, hello everyone. Today, my name is Pierros Ntelis, and I'm an independent researcher at Aix Marseille University. And today I'm going to talk about new avenues and observational constraints of functor functions. Basically, I'm going to focus on this recent paper on factor functions that I have worked on since 2010 with my collaborator Adam Morris. And here, basically, you see a cartoon about the basic idea of what functor functions can tell us, which is basically a new way to view the energy of the universe. And this is described simply by an object that can pass through a certain three-dimensional region. And you can have different kind of energies at different space, or different kind of functions in different space. And the other part of the talk, which is what? Here, yes, here, is about a more general idea about how to compute N-correlators for Nt objects in extra dimensions that are divided into time extra dimension and space extra dimension. My outline of the talk is the following. I'm going to talk about what is built by theoretical cosmologists recently. Then I'm going to describe this new idea about functor of functions, a guide to build models of FA, functors of functions, and their predictions, which are the axionic fleet fluctuations. And I will show you some simulated constraints of this. And on the other part of the talk, I'm going to talk about extra dimension of time and space manifolds, where you can build in endpoint correlation functions for N objects, and with or without contaminated targets. And I will apply that to large-scale structure, which is mainly cosmology, and also to some simple derivations for quantum field theory. And then I will conclude and give some outlook. So recently, what is being developed in general is theoretical models that are based on Lagrangians. And in cosmology, we are based on general relativity, which is a unique theory of a massless graviton. And then we can build other models by either breaking the assumptions, or by adding some additional field, or by adding massive gravity. Now, when we add an additional field, this might be a scalar, a vector, or a tensor. And the most popular models are the easier one, which are basically the Hordensky, where you add one scalar, 1 degree of freedom. And from that perspective, you have either flavors of this kind of model, such as log, Quintessence, Brandt-Dickens, F of R. And F of R, they are the ones that are very popular in cosmology, at least. And then from breaking assumptions, basically you can have extra dimension, breaking the assumption of isotropy and homogeneity, or the locality. And according to all this, now we have found this new idea of how to build functor of functions, and this produces even more models than the one that we have studied so far. Now, let's recap what the theoretical cosmologists are mainly building. They build Lagrangians. So they take mathematical concepts and they add them to produce massive gravity and additional fields to break the assumptions within the Lagrangian, which also includes the integral of space-time. And also all this done by this part of the equation. And the new idea is to think of some more generic arguments of how to build the other part of the equation. And this is the idea of functor of functions, and how we can build actions in a different kind of space, mathematically first. So basically, functor is the generalization of the concept of a functional, and a functional is the generalization concept of a function, as we all know. Functors are not very popular, but they have been built since 1800, I think. And now they have a lot of ideas where you can see they are applied to Feynman diagrams and some other physics as well. And here we applied it to action. Action in physics is basically the quantity which is the product of energy with time. And what tells us, this quantity tells us that the amount of possible ways of a particle can travel from one point to another within a certain region. And the factor of functions, they use this principle and generalize it. And basically, you can predict with these concepts the existence of an actionic fluctuation and field particles, which is an analog of the energetic fluctuation and field particles in nature. So here you see the basic equation. And from the left part, yes? Okay, thank you. So basically, this concept of actions can be generalized, and you can build 7 kind of actions, and this is going to be a subset of an integral of a space of functions, and this would be basically a subset of the full space of all the actions that we can think of, basically. Functor of functions. Again, this is the equation. The Lagrangian on the left part is energy of matter, and then the action is the time integral of L, or the space-time integral of L, which is the number of paths of a matter. And we can build a whole category of set of functor of functions, and this includes GR and quantum field theory, for example. Now, what we can build, let's see, this is the action, the set of functor of functions. We can have effective field theory, which is can be basically an integral, or an integral with some kernel, or some functional of an action, and some other functional of, again, of an action, and then we integrate that to build a new concept. And basically, what else? You can also put tensors of actions, so you can take an action and you can build a tensor which the elements are actions, and you can use that as a new action to build then equations of motion, or you can integrate that and then build different types of actions. And that's it. So this is an example. That's a very long equation, but basically it's a demonstration that an action can be basically written in a different kind of form, which is basically the action from 0 to an action S of the infinitesimal element of an action. And if you take that the upper bound of this integral is the action of GR, basically you can integrate that and gives you the simple GR. And you can have, as always, the curvature component and the matter component. And here you see the details of this action. Now you can do the same with strings. A string, again, is described by this type of action, where you have the path of a particle integrated over this space-time, two-dimensional space-time sigma, which has a certain metric and curvature, and also you include the metric of the space-time. And this, if you put that in the top of the integral, then you can have then the functor of functions, which is basically, in this case, a simple integral of functions, can be simplified to a string one. So another example can be built with an action that is not known yet. So basically, you can build an effective field theory, and a simple model of that would be you need to multiply with a factor, basically, a beta factor, the action of R. Then you can add some constant here that when you do the optimization of this equation, it can go away. But also you can add an action, which is an exotic one. And if you do the optimization, basically the principle of least action, you can do the variation, and you end up with this type of an equation. And this type is led with the following properties. Here you can see the left part, which is a general relativity. And on the other part, where you have the matter component, then you have an effective Newton gravitational constant, which is modulated by this beta function. And then you have an additional matter field, which basically describes this new axionic component. And basically, any new matter axionic component that we can see from Lagrangians basically reflects an axionic component of action, and hence the axionic field fluctuations that I discussed before. And basically, so any matter energy fluctuation is translated to an axionic fluctuation, basically. So this kind of formalism predicts the axionic fields, which are similar to energetic fields, but in another level. Now, another type, a specific model that we can build from this action is that we can build matter fluctuation here that can have this simple form, okay? And here you have the density, and the rest can be a zero component. And then when you have this new matter tensor, it will include the fluctuation of the Lagrangian here on the time component. And then this can be connected with the W, which is the known equation of state of the universe. And basically, when we constrain the W, we can constrain this kind of models. Now, we can build another axionic field. Basically, we can have quadratics of an action. And also, this can be modulated by another model, another parameter here that can be used so that you can have the same units everywhere. But this will lead us to new kind of modified equations. And basically, you start with the stationary action principle, you make the derivation, and you end up with this type of equation that also contains some kind of integration inside. And how we can interpret this kind of integration again? This can be interpreted also as a modification of the gravitational constant. Basically, the effective gravitational constant can be described by this kind of equation. Of course, we haven't seen a lot of deviation of the gravitational constant, but we can see that already this model produces some new models for in the case that we find such a case. And also, these are simple models that I started in this first paper so that can see if there is something interesting inside. And then I would like to explore more complicated models, very sophisticated, let's say, or complicated, I don't know, that you can have tensors and try to see what other type of equations of motion you can have. Now, another simple example is the following of axionic field. Basically, here I use this very simple action, which is linear with an action S1. And basically, you can build a simple model, which is basically an exponential. And imagine that in the future, we would not need to solve by hand analytically, or we can solve analytically what are the equations of motion from an action, but this will be reflected directly to what is the functional form of an action. And if you assume that, then you can build this kind of model. And then you can put the data that are transformed directly from galaxy observation or from collision of particles, and gives you exactly what are the constraints on the parameters of your model, basically. And by using a simple simulation with a simple likelihood, you can build the constraint to these parameters, which is a simple exercise. And this is a kind of simulation of action effective field theory, which is a subset of all these new functor functions. And here you can see these beta functions that I discussed before. This can be a physical parameter. This can be a nuisance parameter, another axionic parameter that constrains this and this constrain this kind of models. And these are some observational physical parameters, F1 and F2. And you have also some nuisance. And basically, you can have the likelihood of this kind of models from your observational data to this kind of models. But here I used an approximate solution of actions, but actually you can build the equations of motion and then translate all that to what is the model of your action. And now here it's a bit dense slide, but the main idea is that here I have built in a new perspective, let's say, what we know so far for the observed universe and the action that describe this observed universe. I assume here that I can have this part, which is the Hilbert, the Hordensky action, which is kind of popular in modifications of gravity models, but modulated by a parameter AH. And then you can also add some other exotic action, and this can be also modulated by some parameter A. Now, I analyzed the Hordensky. The Hordensky can be built by the first three Lagrangians, and then you can add the Lagrangian and then therefore the action for cold dark matter, for gravitons, for black holes, for neutron stars, for gravitational wave sources, for the standard model of physics, the Higgs, the strings, and some exotic. And you see all of this can have like a parameter at first order to see if we have deviations of the parameter 1, then we can see that we have deviations of our standard model, and basically that's how we can start see if we have some interesting fact about these models. Of course, then we can build more complicated actions and try to feed this to the data and try to see what we can learn from the data about these functor theories. That is this slide. Then I have details about the definition of all this equation. And basically, you can see here that this is basically included to the new set of functor functions, even the simple case of the standard model that we know so far about the universe. Now let's see an easy interpretation about this action. Let's see this box, which is a room, and we have an entrance here, an exit here, and we have a cat. Then the cat can have different kinds of paths in order to go from the entrance to the exit. And therefore, let's say that these are n. In the case that we have a column, we have a restriction, so then the cat cannot pass from this point. And basically, this can be n minus n, the amount of paths that the cat can travel from the entrance to the exit. And therefore, since these two rooms, they are separately, you can see that there is a deviation of space. So we can have deviation of the action between different spaces. So we have a fluctuation of function, and therefore we can have a fluctuation of a field of an action in space, and then you can generalize that to extra dimension. And this is the first part of my talk. And there's actually an actionic field everywhere, according to this picture and to this kind of formalism. So another example is that when was before COVID, we had an actionic field like that. And basically, we have many ways to travel from this region because we have also the sea, we have flights, we have also cars. While here, which is only land, you have less action, less paths to go from the south to the north. But during COVID, we have less people to move around due to the restriction of COVID, and therefore this actionic field was had lower fluctuations. So you can see not only space but also in time, a simple example that of this change, basically. So the conclusion of the first part is that the functor of function theories is basically a whole set of new actions, which are called the functor of function exist, and they can predict the actionic field, which is basically reinterpreting the concept of energy fields, and such as the cat motion in distant rooms with different decoration of the room, let's say. So that's the conclusion of the first part of my talk. And for the second part, I allocate some time to discuss about extra dimensions on extra dimensional manifolds with endpoint correlation function for Nt objects. And the basic idea is the following, that in an experimental setup, you can have your target, okay? And this can be described by an extra dimensional target manifold. and you can also have some contaminants of your sample. So therefore, you can have contaminants from earlier times, which is high Z, or late times, lower Z. And therefore, this can be described also by a d-dimensional manifold. Of course, in now observation, we consider always one time and space. Even worse than that, we translate the time and the radial distance into redshift. But I thought it would be interesting to build all the necessary tools to describe about observation in extra dimensions, because by building these new tools, maybe we can find also experimental ways to experiment and build new experiments in order to unlock maybe the possibility of extra dimensions. And that's the effort of this work, basically. So I assume here a model of line element of an expanding perturbed homogeneous isotropic anti-decimal manifold, which is written by this metric. Here you have the scale factor, the basic exponential, which gives you the perturbations, the spatial part and the time part in extra dimensions, basically, from dx. And here I assume also a comoving time component. Now, an endpoint correlator of an object in a d tau dx manifold is going to be described by the tensor multiplication of this manifold, and is going to give you like a complex number as an answer, because that's what an endpoint correlator functor does. And by assuming some isotropy and homogeneity on this extra dimension, you can have the average, the statistical average over the realization of O object, while S and X are absolute and relative position on the manifold. And again, here I have assumed the tau as a definite temporal position. Now, how do we build our observable? I can have many targets, right? So one observable in tau time and X space is the sum of this observable of the target in time and space. Now I can decompose each target observable by universal observable at some initial time. And then the time component is the decomposition of this function can have the time dependence and the X dependence. And of course, if you have n targets, you have a sum of that. But since you can assume that this also is in a one boundary, and then you can also put all of your time and space evolution on this sum. Now, when I have an endpoint correlator, I can put back to this equation, and then I can have this type of observable of an endpoint correlator. I have my observable at an initial time and boundary in extra dimensions, and then everything can be all the evolution of time and space can be described by this factor here at the power of n. Although this assumes also that you have only time evolution, and this is useful for cosmic microwave background in some approximate observations, where you can assume that the cosmic microwave background produces this baryon acoustic oscillation, that this space component doesn't change with time. And basically, that's why I have made this approximation here. And therefore, this complicated endpoint correlation function results to this type, which you have this part on an n power. Now, I can have the target observable and the contaminant observable, right? Because when you make an observation, you don't only have a target that you want to see, but there are some contaminants in the middle, and therefore you have to do some kind of modeling in order to extract the important information. And this has been done in 1 and 4 dimension by a recent, not recent, 2014-15 paper. And basically, I took this equation and I generalized it in time and X dimensions, basically. And also, I have assumed some different kind of formalism to describe this decomposition of time and space. So in this case, I have, again, the observable at the universal observable at some initial time and boundary. And after that, sorry, I have to take a small break, and I will describe that in 2 minutes. No, it's okay. Okay, so the observed quantity basically is that with the sum of the decomposition of the target, which shows the evolution in time and space. And then you have another big component, which shows the dependence on basically the contaminants. And here, this F factor is basically the contamination of your initial field for each target. And you can have, again here, multiple contaminants. So then you have to take that into account. And this results as it is. You have this type of equations here. And then here you have also a modulation of your signal according to the contaminant factor, the evolution of time and space of your contaminant factor, and also this gamma factor, which is basically the transformation of the time and space of your actual target observable in respect with the time and space of the observable of your contaminant. Now that I have this quantity here, I can basically, so basically what is your contaminant factor is the amount of contaminants for each target over all of your observables, basically. Now, all that I can name it as df, basically is the decomposition of time and evolution of your observable, and your f, the factor of contaminants. And basically I gave these two names due to the fact that you have d and f inside this equation, but you can use a different name. I used this formalism at this point. And then under the assumption that the growth of contamination factor is basically only time dependent, you can have this type of simple observable. So your endpoint correlation function in time and space can be built of your observable, of universal observable at some initial time and some boundary space, times this factor here that contains your modulation of your signal according to your contaminants in extra dimensions. Continuing that, now I will apply these notions basically to either a large-scale structure or a quantum scale structure. I start with a large-scale structure. Here you see, as usual, we can have multiple observables in the universe, such as galaxies, quasars, Lyman alpha forest. Now we have also gravitational wave sources, such as the position of supermassive black holes and so on, neutrino, whatever observationalists quantify and categorize these days. And this can be the sum of all these matter fluctuations, basically. So the matter fluctuation of the observable in time and space is basically the sum of all of your target matter fluctuations. Now, you can also do that for cosmic microwave background, which includes also the cosmic infrared background. And here I use a slightly different nomenclature than the standard literature, because I wanted to somehow define a new term for that contains both of these notions. You can also consider that as just cosmic microwave background signal, where you have the temperature fluctuation, the E polarization and B polarization for both CMB and CIB. And you can put basically all those signals, cosmic microwave infrared background, and also large-scale structure in one main category, which is basically the cosmological observables or the observed large-scale structure, if you wish. Here I'm going to use the observed large-scale structure to mean all of those observables. Then you can build your observable, matter observable, as the matter observable at some initial time and some boundary space, and you can have this FBD now component, which FBD stands for the functional of tensor of contaminant factor, bias, and growth of structure. We know that the our observables, they don't only have contaminants, but they also have some kind of bias, which is already quantified by the experiment. And therefore, now you have a slightly changed definition of this decomposition function, which contains both the contaminant factor of each target from each contaminant, the bias of your target, and the time evolution of your target. And this also modulated again by the time evolution of your contaminant for each target, the bias of each contaminant for each target, its factor, the contaminant factor, and again the space-time translation, the Jacobian basically, is needed here. And you have this kind of formula. And this basically describes, in a sense, it describes your observable at extra dimension for large-scale structure and how this is modulated according to contaminant and bias of your target. And when you have this simple observable, you put it to the statistical average for your endpoint correlation, which is a simple textbook calculation. And then you can have a prediction about the endpoint correlation, which if you take the ratio with the endpoint correlator of your matter at some initial time and some boundary, this would be equal to this kind of functional here. So if you have, make sure that you have a very well-known endpoint correlator at some point in the universe, or you can make the assumption that you know exactly how much is the initial and the boundary of this endpoint correlator at extra dimension again. And then the ratio is going to be this kind of formula that you have to constrain from your observations, basically. And here I have not done yet likelihood analysis, and I have started exploring this kind of functional. And here you can see how this n extra dimensional functional for contaminants, bias, and the time evolution of the matter observable is modulated as a function of redshifts for 1 and 3 manifold. So in this case, I have simplified the calculation at 1, 3 to give some kind of example. Of course, I can build some kind of simulations in order to explore extra dimension of this, but I haven't done that yet. So I'm in the process of thinking further how you can build that. But for the moment, I have made something which is reasonable for people that are currently working on this kind of experiments. And here, this functional you see here is this modulation of your signal as a function of redshift according to contaminants for 2 tracers always. The dashed line, the blue dashed line shows the 2 tracers with 2 correlators. The dotted line, 2 tracers with 3 correlators, and you see the signal is increasing of your contamination, basically. And then the 2 tracers with 5 correlations. And then this is even more increasing. So the more correlations you have, the more contamination it is on your signal, and you have to model it correctly so that you can extract the useful information about your target observable. Sorry, that was without contamination. So already the number of correlators, the signal is increasing according to this function. But if you have a contamination, which is basically here I took a sinusoidal signal with some realistic contamination from observation, but I didn't use actual simulation of experiment, but I used some close realistic experiment. So that's why I use a sinusoidal one. You can see here that is increasing more your signal due to your contamination. And if you have a sinusoidal signal, then you have a modulation which looks like that. If you have a different kind of contaminant, then you will have slightly different, which is increasing. And this is because you consider that your contamination in this case comes from higher redshifts. Now, if you have smaller redshifts, then your contamination is slightly different. The behavior of contamination is slightly different, and I can discuss that further if you like in this discussion. So that was part of large-scale structure, and now I'm shifted a bit on quantum scale. So again, in quantum scale, what is your observable? Your observable is going to be a field that you're trying to constrain. And again, you can write it as a field in some initial time and some boundary. And then you can assume this kind of functional here, where it is basically composed of the actual time and space evolution of your field of your target. And this is going to be modulated by some factor here of the factor of contaminant of its target and the time evolution of the contaminant of its target as with the factor of contaminant and the space-time part. Now, you name this as a correlator of your temporal functional of quantum contaminant factor, basically. And basically, you can add that to the quantum correlators that you are using in field theory. And this would be what? This is going to be the manifold integral of all of your fields at some universal of your universal field. But because you want to integrate over all fields, of course, this is going to be an integral of all these fields as a power of n, if you do the calculations properly. And then you can also have the integral over the manifold of the other part of this equation, which is basically the integral of the contaminant of the contamination part. And basically, you do the integration of that. You have multiple correlators here, and you have also the probability, let's say, of these correlators, which is basically related to the action, time and space, and your field and the contaminant part. So that's the final equation that I want to describe. I didn't do more numerical evaluations of this, but maybe at some point with correct collaboration, I might also consider to do these kind of things. So the main conclusion of this talk is the following, that our current picture can be altered basically by these new theories, the functor of function theories, which can be applied to large scale structure and also quantum scales. And these predict the actionic fields. And also the other part of my talk, which describes extra dimensions in time and space and extra dimensional manifolds, basically, with endpoint correlators and Nt objects. And we can consider extra dimension, contaminated sample in this extra dimension. And basically, we can apply that to large scale structure and quantum scale in order to obtain more accurate results in the future. Of course, there's a continued ongoing work on testing these theories with several observables and telescopes, or from the other side, from colliders, to constrain dark energy, dark matter, Higgs, the behavior of the Higgs, and so on. So I'm open to your suggestions and collaborators, and thank you very much for your attention.
Ευχαριστούμε πολύ, Πιέρο. Σταματάω την καταγραφή.
Ναι, ευχαριστώ.
Για να